So now we're going to get into linear regression. Linear regression is very similar to correlation in a lot of different ways. So correlation looks at the association, but linear regression is some of the formula is similar to correlation, but correlation looks at that association. Linear regression actually builds a prediction model to explain your data. So today, or in other words, the linear regression is a model that predicts the relationship between one or more continuous variables and a continuous response variable. You could actually, this I would say I would take out. So linear regression, it always has a continuous response variable. So you can have variables that are not all continuous that are explaining it. So that was a typo. But so one or more variables explain a continuous response variable, and we would call these predictor variables. Today, we're going to go over simple linear regression. Almost in no cases will you actually use simple linear regression. You would do something that has more than one variable as your predictors. However, this is a lot easier to understand. We're going to get this get into multiple variables, predictor variables, and not the next class, but the class after that for our statistics sections. I do think it's important to go over the most simple explanation, even if it's not highly used, and then we can build on that information and learn more about the other cases. So we're going to do the simplest case here. Yes, it might not be used in practice, but this will help us understand what is actually used in practice. We will cover multiple linear regression a little bit later. So this I believe was included in the first statistics book I ever read, and it really helped me understand this. So I went back and found it and put it on here. So in this case, red points here are the actual values. So the linear regression, what it does, it creates this blue line here. Why is that chosen as the blue line? So we look at what we call this black line here is the error. What that means is the difference between the actual values and the prediction line. So all of these are straight down. So when we look at the error value, you can see this down here. So this again, the I is 0.1, 0.2, 0.3, 0.4, and then E stands for error. Y1 is 0.1, 0.1, 0.2, 0.3, 0.4 in our data set. So the different rows, and then minus the prediction value. Hat always means predicted. People call it Y hat. So this is always means a predicted value. So when we look at the error, it's Y1, so the actual value minus the predicted value. In order to build a prediction model, we looked at the squared error. So this is the error formula. In order to build a linear model, they find the math finds this blue line that minimizes the squared error. So you see that here. So the goal is to minimize that squared error. So this comes back to it. So our why do we want to square that? Because some values are going to be below the prediction line, some values are going to be above. If we just looked at Y1 minus Y hat, we would have some above and some below, and that wouldn't give us much information about how the prediction line deviates from actual values. Say you had a bunch of values up here and a bunch of values down here. That would be worse at prediction than the one that's here, yet it might show that it was better if we didn't have a squared value. That basically makes it similar to an absolute value, but we also want to use the square for another reason. The squared values penalize large differences between our predicted and our actual prediction model. So things that are really large, when you square them, they're going to be really large. A difference that's much smaller. So if you square this it's going to show a larger difference than if you square this value here. So it then penalizes these far out values a lot more than these smaller values. So that is the whole goal, and that is how we decide the prediction model here. And that's what R is doing on the back end. So are there any more questions about squared errors, and we're going to get into the prediction model formula in just a second. Okay, good. So if you go back to your algebra class that you took in high school, that a straight line always has a formula that is similar to this. So this is the y-intercept, this is the slope, and these are your x values in your data set. So I define them here. So when we look at something like this, this can be translated into the y-intercept plus the slope times the x values. You might also see it written as y equals mx plus b. In that case, b would be the y-intercept, and then mx, the m, would be the slope. So you can see this written in a lot of different ways, but they all mean the same thing. So this is would be our response variable, and that equals this. So this is our prediction model. This is our y-intercept. So when it crosses the y-axis, that's what y-intercept means, plus the slope times x. So the slope looks at how steep our line is. So a steeper line up here is going to have a higher slope than this line. So we're looking at how high the line is. A horizontal would have 0 slope. A vertical would have a 1 slope. So I'm not going to go over that in more detail. An algebra book can go over that if you need more clarification. But you can also, and this is the most simple prediction model, I would call it, that you can create. So you could create a linear regression prediction model, and you can have a lot more than one variable here that say you have actual values. You make the model in 2017, but you want to make predictions with 2018 data or 2019 data. You could put that 2018 data in these x values, and then we would have our slope and our y-intercept, which are going to be static from our 2017 data. And then we could put our 2018 data in here and make predictions about the response variable. If there's questions about that, we're going to go over that in detail later, so I would want to table that. So back to here, the slope means the same thing as the correlate. I misspoke. The slope means the same thing as a coefficient. If you hear the word coefficient, which is most often used, I just wanted to tell you that it was the slope, because that is something you've probably seen before. So the slope or the coefficient is B1 here. That is relevant here. So when we talk about linear regression, it's always referred to as the coefficient, almost always. So you'll see that this looks very similar to the linear regression formula. It's not exactly the same, but close. So in order to estimate our coefficient, we use our actual values and then the mean of that value in order to get this slope variable. I already went over what this actually does before, so I'm going to kind of skip over this, but this is the formula. And here is how we would find the y-intercept. So you find the slope first, and then you plug that in order to find this y-intercept. That's basic algebra. You've probably seen it before as well. Might not remember it, but it is that basic algebra. So you then use this as our value here. Sorry. And then you use this as our value here. So the reason why a lot of people like to use linear regression, even if it might not be the best model for the case, predictions might be a little better with something else. Depending on your data, it might be a lot better. However, when you give data or results to a stakeholder, it makes sense to them. They kind of often think of this as a weight. Intuitively, that makes sense to them. So they can see that you multiply this value by your actual values, and then you add a constant and it gives you a prediction. That makes sense to them intuitively. They might not understand the math, but it can be easily explained. In a lot of cases, at the different companies I've used, we have defaulted to this just because it made sense to the stakeholders. Whereas if we used, say, a random forest, it would have been a lot harder to explain and less acceptable. So are there any questions about this before I move on? What do coefficients mean? So you're going to see a lot of similarities between this and the correlation coefficient. If our coefficient is positive, just like when our correlation is positive, it means the predictor rises as the response variable also rises. So positive is going this direction, negative would be going this direction, just as we saw earlier in the slides. A larger coefficient means that there is a stronger relationship between that predictor variable and our response variable. So that's what, and if something's really small, it's going to have less of an impact. So one thing that I should bring up, we're not going to go over how to deal with this, but say you have a linear regression, you have median household income in our linear regression, but you also have the percent that have a bachelor's degree in our sample. So that's a problem because it's automatically going to weight the larger numbers with more of a weight. It's going to see that they're more important just because of the math behind it. It's something to be aware of. And in machine learning, we'll go over it a lot more. And even with this, you can use this technique. Technique is to standardize your values. Either fit those values if they're very, very different between -1 and 1, or we went over the z-score. You can make them put them on a z-score line. If you want to know more about this, we're going to get to it later, but I do want to mention it because it can bias your results and bias the conclusions that you have. You should be careful and use things that are on a similar scale. So I picked this data for a reason. The data has a similar, it's not all that different from one another. Mortality more so, but probably not a big enough difference to make a huge impact on our results. But all of our predictor variables are percents. That was by design. Life expectancy is on a similar scale, and mortality is a little bit different. So you would want to be cautioned, and you might want to standardize something like this. The other thing that we will get to eventually, you can use ridge regression or lasso. It helps, it penalizes coefficients that are higher so that you can make sure that there's a relationship. I'm not going to get into that either. You can do some reading on the side if you'd like to, but it's something to keep in mind. We again use the t-statistic in this case. In this case, it is the slope over the standard error, and we can get a t-statistic for every coefficient. And then our degrees of freedom is n-2. So you'll see multiple p-values, one for the entire model and then one for each coefficient, to look at the relationship between each individual variable. So in order to get that p-value, they use the t-statistic and the degrees of freedom, which is a number of observations -2. Okay, I am going to go in and show you what the output looks like, and then I'm going to go through the assumptions if I have time. So we're going to, at this second one, use heart disease mortality rate, and we're going to use that as our data. Since we already went over this with correlation, I think it should be pretty obvious. I'll do this first. So in this case, I made these box plots. Box plots are especially useful for finding outliers. These outliers here, I made a judgment call that these outliers were too far out, and I got rid of them in the mortality rate. As Michael says, when there's an outlier, you have to get rid of the entire row, because say you have a missing value for your predictor, it's not going to give you a prediction anyway. It's going to remove it from your model no matter what you do. So I explicitly got rid of it here. And I also got rid of this point here because that's very clearly an outlier and possibly even a mistake. So it doesn't add to our knowledge. So all I did here is I remove those extreme outliers. So we're going to examine our data. I did adjust this code a little bit, so we need to change it to that. So draw this out. If you want to learn more about graphing, our class that I taught was on ggplot, which is I'm using here. So this is just a scatter plot of our two values. So we have average heart disease mortality rate down here and the percent below the poverty line here. We're seeing this is pretty randomly dispersed. It's dispersed in a similar way and it's linear. We're going to have several ways of checking that and then adjusting if needed. So, but first, since we just went over this, you see a lot of numbers here that I have not gone over yet. So a lot of this, like when we're going to talk more about p-values, we're going to talk more about the r-squared and the adjusted r-squared and our F statistic. All of that's going to be covered in the next class. So, and we'll probably cover a little bit about standard error as well. So I'm not going to go over that today because I want to talk more about building it. So we're seeing here our estimate. So this is our y-intercept. So if we were finding a prediction, we would want to add that to all of our values. The percent high school graduate percent that have a graduate high school degree or higher is what that is. Our estimate, we're seeing 1.48. So if we were finding a prediction, we would multiply this by all of our values. We're seeing that both are highly significant. The intercept matters just because it's a default value that you add on to each one of your values. But the significance probably shouldn't concern you if it's not. But this is the information that we want to see. So when we see this p-value, this means it's very low. When we see that -16, that means the percent of the high school graduation, that variable has a very strong relationship with the heart disease mortality rate. Again, correlation does not equal causation. It applies in this case too. So say you added and we might actually use this as an example later on so we can use the same data. You could possibly add percent with a high school graduation or higher, percent married, and the percent below the poverty line into your model. And it would explain a lot more of the variation in heart disease mortality rate, more than likely, because obviously there's a lot more involved in explaining this than just one variable. We're going over just one variable for today because it's simplified and it's easy to understand. We'll get to more variables later and how to evaluate those models. But that's what we're seeing here. Are there any questions about this minus the evaluation pieces?